welcome back, everyone. It's my pleasure to introduce Bastian Köpke, who is a PhD student in Sergei Golic's group in Münster, and he's going to talk about generating efficient FFT GPU code with Lisp.
Hi, thank you. I'm going to present some work that I did together with Michael Stoiber and my supervisor Sergei Golic, and we did a case study on generating code, FFT code in Lisp, Fast Fourier Transform code in Lisp. And we decided to look at Fast Fourier transforms because, first of all, they are used in many fields, like imaging, machine learning, physics simulations, and even more fields. And additionally, they are usually not that easy to implement efficiently. So it's interesting to see whether we can express FFTs on a high level and then generate fast, efficient code from them. For that, we use Lisp. Lisp is a compiler with a data parallel high-level language in which we can express applications on a high level. We only say what we want to compute, but not how we want to compute it. And then the Lisp compiler takes these programs, these high-level programs, and rewrites them into low-level target-specific programs that then specify, for example, parallelism, whereas sequentialism, how to use memory, and these kind of things. From these low-level target-specific programs, we can generate code for different targets, like OpenMP for multi-core CPUs or OpenCL for GPUs, and so forth. And the data parallel high-level language of Lisp uses algorithmic patterns like map and reuse, or split, where split simply takes a one-dimensional array and splits it into chunks of size n, creating a two-dimensional array, or join, where a two-dimensional array is just joined together into a one-dimensional array. Zip creates pairs of elements from two arrays, element-wise, and pad, for example, pads an array, so it extends an array by the array elements from the other side. So it wraps around the elements again and again. Transpose treats a two-dimensional array like a matrix and simply transposes it. And with these patterns, we can already express in Lisp the dot product that we saw earlier as well. And here, zip is defined slightly differently. We don't have zip width, but still we zip our vectors v and w. Then we map the multiplication, and then we reduce all the results. And we can define this Lisp function now and reuse it in other Lisp functions again. So for example, for the matrix vector multiplication, we can reuse our dot product definition and define a matrix vector multiplication and simply map the dot product with V to every row of our matrix M. And our question now was, how can we express fast Fourier transforms in Lisp this way? And in order to derive an encoding of fast Fourier transforms in Lisp, we first had to look at what is a fast Fourier transform. So fast Fourier transforms are fast algorithms for the discrete Fourier transform. The discrete Fourier transform is simply a matrix vector multiplication with a dense matrix. So in this DFT matrix D, there are no zero entries, there are elements everywhere, and these elements are defined by a formula. This formula depends on the row and the column the element is in and the size of the matrix. So what this means is that we can compute the element at a given position by this formula. The details of the formula don't matter, it's just important we know all the elements in the matrix. Okay. And now the idea for fast Fourier transforms is that we can decompose this matrix into sparse matrices. And these sparse matrices have a lot of zero entries, of course. And by then cleverly implementing the multiplications with these sparse matrices, we can reduce the computational complexity of the entire algorithm from O of n squared to O of n log n. And these clever implementations, of course, try to avoid or completely avoid multiplying with zero. Okay. So, these sparse matrix decompositions, there exist a lot of different versions of it. For example, the Stockham and the Coulé 2K FFT are different versions of fast Fourier transform with different decompositions. But these decompositions can be expressed, as shown here, with mathematical formulas consisting of smaller other matrices that then build up the larger decompositions. So just as an example, in the blue square here, this represents one matrix, but it is described in terms of another matrix B with a Kronecker product, an identity matrix. Then there's somehow a matrix pi that is transposed and so forth. But we see that there's matrix multiplication here, there's a Kronecker product here, and then we have these matrices. And even for the other FFT, it's similar again. We have, again, Kronecker products, identity matrices. They are just applied in a little bit of a different way. And so what we did now is we looked at how can we abstract these different components and express different FFT versions with just some definitions. And we say that a decomposed matrix that we see here, so from before here, the matrices are multiplied and one matrix multiplication is a pass. And these passes appear here again. Okay. So for this talk I'm just going to focus on Stockholm FFT, but for Cooley 2K FFT it's very similar and we can reuse our definitions that I will create now. So for the Stockholm FFT, we can immediately start defining a function that says, okay, we want to compute the Stockholm FFT by just saying, okay, we need an array of these R's that are just parameters. What they exactly do isn't important. From these R's we can compute n, we can even compute these elves, so we have every information that we need. And also we need v, the input vector that we want to compute our Fast Fourier Transform over. And then we say, okay, we want to apply a lift function, stock pass, to v, and then we apply one stock pass after another until we have computed the entire Fast Fourier Transform. And as we can already see, the stock pass function is reused over and over again, and we simply use different parameters. So this tells us that we definitely want to encode the stock pass, and after that we can already express FFTs in lift. In order to express the Stockholm pass in lift, we look at the mathematical formula again, and again the details are important. We just see that we have two matrices basically that are multiplied with v. We have what we call the combine matrix, which combines values from v into new values. And we have what we call the permute matrix, which simply reorders values in v. And again, we can immediately express this by defining a lift function, which we call stock pass, which we used earlier already. The function itself takes only, later when it's instantiated with R, L, and N, it takes only the input vector v, and then applies the permutation, and then applies the combined matrix multiplication. And again, the next step is to implement these functions. But before we do this, we note that in both matrices are built up out of the Kronecker product. The Kronecker product takes two matrices, and then A and B, and then multiplies every element of A with B, and therefore creates a larger matrix in the end. We also note that on the right side of the Kronecker product, in both cases, we have the identity matrix. So what we can do now is we can use this domain knowledge to encode a multiplying matrix that is created by the Kronecker product with an identity matrix on the right side, and therefore we can save a lot of arithmetic operations. Just to show an example on how this would work, so we have a matrix that is created by the Kronecker product with an identity matrix on the right side of size 2. The matrix looks like this, the empty space are zeros, and now we multiply with v and get the result. And this is similar to multiplying A with a vector v0, v2, and A with a vector v1, v3, and then using the results in the result vector properly. Okay. So we can express this in lift by defining again a new lift function, cron ID rv, that especially that says, okay, we have the Kronecker product with an identity matrix on the right, and we can simply use the lift primitives to first group every mth value for an identity matrix of size m. By splitting M and transposing, that groups the values that we need in one, and then we map again a new lift function that encodes multiplying the matrix A with a vector. And afterwards, we ungroup everything again, and then we get the result. Okay? And again, we define this in Lisp. We define a function that takes this other Lisp function that defines and encodes multiplying matrix multiplication of A. And sorry, matrix vector multiplication. Okay. So now we have expressed this part of the formula, but we still need to express multiplying B with the vector, and we need to express multiplying this transpose pi. I'm just going to assume that we have already expressed the multiplying transpose pi. It's not that interesting, the B is way more interesting anyway, and if you want, you will see how pi is expressed anyway later on. Okay, yeah, B and pi later, so B now. B again is a sparse matrix, and again we want to avoid multiplying with 0 entries. So what we did is we represented B in a way in this array, and this array contains matrices, and these matrices do not contain 0 entries. And now by cleverly reordering our V again, we can simply multiply these smaller matrices with parts of V and avoid multiplying with 0 completely. Okay? And again, we can express this in Lisp by defining a new function, mult B. And first we use our representation of B. The details of this I don't want to show, but it's not that interesting anyway. And then we map a complex matrix vector multiplication. It's complex because B is complex, V can be complex, it's a Fast Fourier Transform, everything can be complex. We note also that B can be expressed in a different way or seen in a different way. B can be decomposed one more time, even further, into a matrix consisting of a lot of these smaller D matrices, these DFT matrices that I showed right in the beginning, and a diagonal matrix consisting of so-called twiddle factors. And the idea for encoding this would be to separately encode first the DFT matrix multiplication and then element-wise multiplication with different twiddle factors. Looking ahead a little bit, this can be really useful for us because we can pre-compute these twiddle factors, which are computed by sine calls and cosine calls and these kind of things, which can be really slow on a GPU. And we can pre-compute these values and then load them into constant memory and reuse them during our computation without having to call cosine and sine functions. And the drawback is that we have more arithmetic operations. So, okay, we have now expressed everything that we need to generate code. We had already expressed everything that we need to generate code a slide earlier with mult B, but now we have a second version that we can use also and see how good our code gets. And before any code is generated, what the Lisp compiler does is it inlines all the Lisp functions that we have previously defined. So we had the stock parse, and in stock parse we called the combine and the permute, and in permute we called other Lisp functions, and all these Lisp functions are inlined now. And these inline functions, this large expression, is now rewritten by the Lisp compiler to introduce parallelism, for example, or to do slight changes to the algorithm itself. As an example here, we have again, this is the same expression, we have the high-level FFT parse, and this is rewritten into a low-level FFT parse expression that looks something like this. A lot of things stay the same, but some things change. For example, some maps become map global, which just says, okay, the function or the map should be executed in parallel, distributed over all the threads running on the GPU. Map sequential would be just sequentially compute a map. Reduced sequential is similar. Not every map is rewritten though. For example, this map here is not rewritten, and that is because the function inside of the map will not ever, will only affect how data is accessed. So we don't ever have to create a for loop, for example. Okay? From the low-level FFT parse, we can now generate code. So from this code, we can generate OpenCL code that looks like this. The for loops correspond directly to the different maps and reduces, and the indices, for example, correspond to the joins and transposes, they all collapse into one thing, into index computations that tell us how to access the data in the end. And this code we can now execute and we can measure the runtime for it. We did that for the Stockham FFT and the clFFT that I showed briefly, and for some different versions of them, and we compared with clFFT, that's an OpenCL library implementation for FFTs, and with cuFFT, which is the CUDA implementation by Nvidia for FFTs. And we measured on an Nvidia Kepler GPU and an Nvidia Radeon GPU the runtimes in milliseconds. The naive version of the Stockham is what we saw earlier with mul-b. The coalesced version is a version where we rewrote the data accesses so that the hardware can coalesce memory accesses, and the twiddle factors uses this coalescing rewriting and also this twiddle factor optimization, which I showed earlier. And as we can see, our generated code on the Kepler GPU is significantly faster than clFFT, but still a lot slower than cuFFT. cuFFT is very fast, about 4 times faster still. And on the AMD Radeon GPU, we cannot measure the cuFFT, of course, because it's CUDA, it only runs on Nvidia GPUs. But we can measure against the clFFT and see that we are unfortunately still slightly slower by a little bit less than 50%, I think. So, again, in conclusion, we are able to formulate abstractions for FFTs that can be encoded in Lisp. These abstractions closely resemble the mathematical definitions. We could simply rewrite the mathematical definitions with other symbols, and then it would look very mathematically. Our generated code is faster than clFFT on the Nvidia GPU, but still and less than 50% slower on the AMD GPU, and cuFFT is almost still 4 times faster than our generated code. Thank you.
We have time for a couple of questions.
Yeah.
It's a very obvious question and maybe a little bit mean to you.
Okay.
Do you have some intuition what this factor 4 with the cuFFT is causing?
Yes and no. So there are still some things that we couldn't express in Lisp yet. For example, go there really quick. These matrices consist of a lot of smaller DFT matrices, and these can be implemented very efficiently manually by exploiting memory structures and these kind of things. And this is something that I have not been able to express in Lisp yet. So that is a very important part which is still not expressed, and therefore we are definitely slower. I don't think that just changing this though will really improve the performance that much that we are 4 times faster.
The other question I had is more abstract.
Okay.
So you found very beautiful functions to express what the mathematicians are doing, and they usually just write long formulas with indices and so on. Yeah, and your abstractions make this very clear what it is. But at the lower level, you have a similar problem, namely that you want to map the abstractions to the geometry of the memory, like what is contiguous and how long should your chunks be and so on. Are these two separate things in your opinion, or is the language handling both at the same time?
They are, I'm not entirely sure if I could understand the question correctly, but they are, so how memory is accessed definitely depends on the algorithm choice, the FFT choice, but it can also be rewritten on a lower level, just by looking at the splits and joins, but then we need rewrite rules, formal rewrite rules that know how to rewrite everything.
Yeah, so I didn't memorize all the function names, but it sort of seemed that at the lower level during your compilation, you see, you could achieve all the memory optimizations in almost a similar fashion as you're dealing with the initial problem decomposition to chunk things up in the right way and so on.
Mm-hmm.
You said somewhere though that you were sort of making some manual subtle corrections to,
Yes.
to refine things further after compilation,
Yes.
more or less, right?
Yes, yes.
Could you say a little bit more about the Lift project?
The Lisp project has I think been invented by Michael Steurer. It's a compiler together with a functional language. The ideas, I guess, can be described a little bit similarly to what we saw earlier with Accelerate. But here we have this specific language. It's not, it's embedded in Scala, but still it's its own language. And you have these patterns that we saw and the lift functions basically, and this is all there is. So you have again this idea of you restrict to a certain set of patterns and language constructs to achieve high performance in the end.
Did you compare anything? Did you do FFTW? Because that's what I would automatically reach for if I was doing.
As far as I know, FFTW doesn't work on GPUs?
No, but you've got CPUs at there.
Yes. But I haven't compared it on
okay.
CPUs. No.
Is this in relation to the Spiral project? It kind of reminds me of that. Oh.
Yes, there's definitely a relation to the Spiral project. When I started this, they hadn't written the last paper they brought out yet. So Spiral was developed with FFTs in mind, and Lift is developed for general purpose applications. So that's the big difference. So for Spiral, the question is how can we improve the performance of FFTs specifically, and for Lift it's general purpose, and can we even do FFTs?
Was there some overlap between people or
No.
no?
Any other questions? Then let's thank the speaker.